Hey, hello. Let's start today's class. So in this class, we will delve into the application of the continuity equation. We will apply the continuity equation to gain a deeper understanding of ambipolar transport and interpret this ambipolar transport through the continuity equation. Additionally, we will utilize equations that describe ambipolar transport to calculate the current components generated by electron and hole pairs. Finally, we will conclude class by examining several examples applying the ambipolar transport equation. The continuity equation derived in the previous class is as follows. So in ambipolar transport, electrons and holes always move in pairs. So we can assume that the concentrations of excess electrons and excess holes are equal, right? Additionally, to simplify the equation, we will assume that the generation and recombination rates of electrons and holes are also equal. Next, the electric field can be expressed as the sum of the external electric field applied from the outside and the internal electric field induced between electrons and holes. However, interpreting information about this internal electric field physically can be quite challenging. Therefore, let's make a slight modification to this equation. If we multiply each term on both sides of each continuity equation, and then add the two equations together, we can obtain the following result. Furthermore, dividing by the common factor, we can see that the derivative term with respect to the electric field disappears, right? These kind of electric field are not exists in these equations. Eventually, it can be observed that this equation is organized into a form similar to the continuity equation. Since the concentration of excess electrons and excess holes are equal, so any notation, so instead of delta N, delta P can be used because delta N is equal to delta P in ambipolar transport, right? And here, D prime D prime represents terms involving the mobility of electrons, mobility of holes, concentrations, concentration of electrons and holes, and diffusion constants. So using the Einstein relationship, the terms related to the diffusion constants and concentration of electrons and holes can be expressed. And similarly, mu prime can be expressed as a combination of concentration and mobilities of electrons and holes. In summary, we simplify the continuity equation for excess electrons and excess holes to eliminate the dependence on the electric field. After simplification, we obtain the continuity equation. That determines the motion of excess electron and excess holes. The diffusion constants and mobility that govern the motion of electron-hole pairs in the ambipolar transports are expressed here. This equation is referred to as the ambipolar transport equation, where D prime is the ambipolar diffusion coefficient and mu prime is the ambipolar mobility. However, understanding the roles of particles in ambipolar transports based solely on this equation can be challenging. So in the following slide, we will explore this in more detail through several assumptions. Okay, let's consider ambipolar transports in a p-type semiconductor. In a p-type semiconductor, holes are the major carriers and electrons are the minority carriers. So assuming low-level injection, the concentration of majority carriers does not change significantly, and the concentration of minority carriers approach the concentration of excess carriers, right? Due to low-level injection, the concentration of majority carriers remains much larger than the concentration of minority carriers, right? So it is much larger than minority carriers. So using these conditions, let's approximate D prime and mu prime once again. So starting with the expression for D prime, when we simplify it, these terms are disappeared because P is much greater than N, right? So because P is much greater than N, so we can eliminate these terms. So as a result, only the term related to the diffusion constants for electrons diffusion constant for electrons remains significant. And similarly, when we apply the condition that P is much larger than N to mu prime, only the term related to the mobility of electron is significant. So it is same for in this case, right? So therefore, in a p-type semiconductor, when ambipolar transport occurs, excess carriers move according to the diffusion constant and mobility of the minority carriers. So it is according to the minority carriers, which are the electrons in this case. So similarly, for an n-type semiconductor, we can rearrange the expression to show that excess carriers move according to the diffusion constant and mobility of the minority carriers, which are holes in this case. So, in summary, in ambipolar transport, the movement of excess carriers consisting of electron and hole pairs is dictated by the characteristics of the minority carriers. Understanding ambipolar transport involves recognizing that electron and hole pairs move in accordance with the characteristics of the minority carriers as revealed by solving the ambipolar transport equations. Therefore, to calculate the distribution of excess carriers in an ambipolar transport situation, one ultimately need to solve the corresponding equation. However, these equations are a second-order partial differential equation involving derivative with respect to both time and position, so making it a complex differential equation challenging to solve by hand. But fortunately, in many cases, considering only a few key terms in the ambipolar transport equation can be applied to specific and crucial scenarios. The ambipolar transport equation generally include five terms denoting different colors, and the table below summarize under which conditions each term can be neglected. In the following slide, we will explore some situations in which semiconductor devices operate under non-equilibrium conditions. First, let's consider the scenario where light is continuously incident on a semiconductor with uniform doping until the excess carrier concentration reaches a steady state. If we suddenly remove the light in this situation, excess carriers will recombine over time and causing a gradual decrease in their concentration. So let's consider the case where a uniform p-type semiconductor without an applied electric field is exposing light. So it is light, exposing light. Then at t equals 0, the light is abruptly turned off. Let's assume that the excess carrier concentration generated by light is very small compared to the thermal equilibrium for concentration. Since it is a p-type semiconductor, the motion of excess carriers is determined by the minority carriers, which is excess electron, right? So, assuming that excess core concentration is constant and there is no applied electric field and no more excess carriers are generated, we can simplify this one, and this one. So we can simplify the equation. We can simplify the equations as follows here. So in the case of low-level injection, we can consider the minority carrier electron's lifetime to be constant. The solution to this equation is as follows. Therefore, the excess electron concentration decrease exponentially over time, and the time constant is the minority carrier's lifetime. In ambipolar transport, delta N and delta P are equal, so the excess Hall concentration is also same. If we graph this, it will look like the following one. On the contrary, if light is absent for a period and then continuously applied thereafter, how will the excess carrier concentration change? In this case, we can expect that excess carriers will gradually increase over time until they reaching a steady state. Okay, so let's consider the same semiconductor as before, but this time we will uniformly illuminate the entire sample with constant intensity light starting from at t equal 0. Since we are illuminating the entire semiconductor with light, excess carriers will be uniformly distributed, right? And there is no applied electric field, right? So they are uniformly distributed and no electric field. Therefore, the ambipolar transport equation can be expressed as follows. The difference from the previous example is that in this case, The generation of excess carriers occurs as we start illuminating the sample. Here, at t equals 0, there are no excess carriers, and as time goes to infinity, it reaches to a steady state. Therefore, if we graph the solution to this equation, it will look like the following graph. So starting from delta n equal to 0, right? Next, let's examine the distribution of excess carriers with respect to distance when uniform intensity light is continuously applied to a specific point until it reaches a steady state. In this scenario, excess carriers just generated at specific points will continue to undergo diffusion, right? Undergo diffusion and recombination, spreading out until they reach a steady state. So considering a p-type uniform semiconductor in the xy plane without an applied electric field, let's expose the region at x equal 0 with constant intensity light. Assuming that the semiconductor wafer is thin enough so that the concentration of excess carriers is uniform on the plane and the low level injection condition is met, excess carriers generated at x equal 0 will diffuse. Excess carriers will diffuse, right? Excess carriers will diffuse in both the plus x and minus x directions and experience recombination leading to their gradual decay. Over time, these carriers will eventually reach a steady state, resulting in a uniform distribution, right? In this situation, what we want to determine is the distribution of excess carriers at a location where x is not 0. Therefore, we can simplify the ambipolar transport equation as follows. Since there is no electric field and the light is only incident at x equal 0, it means that there is no generation of excess carriers at points other than 0. And we are examining the distribution in a steady state. So dividing both sides of the equation by the diffusion coefficients, we obtain the following expressions. Here, the newly defined parameter Ln represent the diffusion length of minority carriers and has units of length. The general solution to this equation is given by the following. Since minority carriers, electrons in this case, diffuse from x equals 0 and undergo recombination with majority carriers holes, the electron concentration approaches 0 at both extremes. From these boundary conditions, we can express the solution separately for x is greater than 0 and less than 0. Therefore, we can conclude that the variation in excess carrier concentration with distance decrease exponentially. Additionally, due to the charge neutrality condition, the concentration of excess majority carriers, excess holes, also decrease exponentially with distance following the same parameter as the minority carrier electron diffusion length. However, since P0, the excess holes generated is much larger, the concentration of excess majority carrier holes remains nearly unchanged. Now let's explore the scenario where carriers are continuously drawn into a carrier sink from one point. We will consider the case where uniform intensity light is continuously applied to the entire sample, while a carrier sink exists at a specific point. In this case, let's examine the distribution of excess carriers. At this time, let's suppose that we have an n-type semiconductor in the xy plane and light is uniformly incident on the entire plane, generating excess carriers uniformly. However, at x equals 0, there are numerous defects are present on the plane, causing excess carriers are drawn into the sink. So the carriers are drawn into the sink. Since there is no externally applied electric field and it is a steady state situation, the ambipolar transport equation can be expressed as follows. So the solution to this equation is as follows. A uniform intensity light is continuously applied to the entire semiconductor, resulting in the generation of excess carriers at a constant rate. Since the generation and recombination rates are equal in steady state, so substituting x with infinity yield the fact that a is 0, and substituting x with 0 allow us to determine b. So we can determine a and b. So ultimately, the solution to the ambipolar transport equation can be expressed as follows. Here, this one, LP, represents the diffusion length of excess majority carriers, and it can be visualized in the graph as follows. However, since the lifetimes of minority carriers differ at x equals 0 and at infinity, the recombination rate of excess majority whole sorry. So the recombination rate of excess majority holes can be expressed as follows. So until now we have considered examples where either time or space change, but in this case, let's think an example that depends on both time and position. So in a scenario where an electric field is applied, light is instantly directed to a specific point, generating excess carriers, and then the light is removed. The generated excess carriers will undergo diffusion and recombination due to the applied electric field. Let's observe the change in carrier concentration in this situation. In this case, as light is applied and then removed, there is no further generation of excess carriers, and the ambipolar transport equation remains with the existing terms. Since the equation is somewhat complex, so let's briefly look at the result. So if there is no electric field, excess carriers will diffuse in both directions, and it can be expected that there will be no significant shifts in the peak position of the curve. Additionally, if excess carriers do not undergo recombinations, the area under the curve will remain constant despite the reduction in the peak due to the diffusion, right? However, in reality, over time, excess carriers will diffuse and simultaneously undergo recombination, so gradually leading to their extinction, and the final concentration will become 0. And when an electric field is applied, the graph will represent it as follows. In this case, excess minority carriers holes undergo diffusion and recombination while simultaneously drifting in the direction of the applied electric field, which is plus x direction. However, a crucial fact is that at any moment, at any point, the concentration of excess holes and excess electrons are equal. As although excess electrons carry a negative charge in ambipolar transport, they move in the direction of the applied electric field, similar to the applied field direction. In essence, in ambipolar transport, excess majority carriers electrons move together with excess minority carriers holes, and their motion characteristics are determined by the minority carrier's force. To summarize, we apply the ambipolar transport equation to three main scenarios. Firstly, we examine the change in excess carrier concentration over time, specifically in a situation where light is continuously applied uniformly, reaching a steady state, and then suddenly removed, right? So in this case, recombination occurred over time, leading to a decrease in excess carrier concentration. Consequently, there were no change in the spatial concentration and applied electric field terms, and only recombination and concentration over time were present. And next, we consider a scenario where light was absent and then suddenly applied uniformly. In this case, excess carriers increased over time until reaching a steady state. So similar to the first case, there was no applied electric field, and the terms for recombination, concentration over time, and the spatial concentration were present, but there was an additional generation term. Then there are scenarios that are involved change in carrier concentration over space. So we focused on the situation where uniform light was applied to a specific point, leading to the diffusion and recombination of excess carriers until reaching a steady state. In this case, there were no terms for applied electric field generation and concentration over time, but only terms for recombination and spatial concentration. Additionally, we explored a case where uniform light was applied to the entire semiconductor, but there was a carrier sink at a specific point, causing excess carriers to be removed continuously. In this scenario, a generation term, which was not present initially, was introduced. And finally, we briefly examine the scenario where change in carriers occurred simultaneously in both time and space. In this case, an electric field was applied and light is instantly directed to a specific point, generating excess carriers. After removing the light, the excess carriers undergoes diffusion and recombination while drifting due to the applied electric field. Only the generation term was absent in this case. Despite the complexity of the ambipolar transport equation, by selectively removing terms based on the condition of each scenario. We are able to obtain relatively simple solutions. So understanding the behavior of excess carriers in non-equilibrium states required equations that describe generation, recombination, throughput, and diffusion. Therefore, we derive the ambipolar transport equation and explore its applications to interpret phenomena related to excess carriers in non-equilibrium states. So in this chapter, we explore the continuity equation and ambipolar transport equation for currents. So using the ambipolar transport equation, we derive solutions for several important phenomena. That concludes today's class. Thank you for the listening.